Given the magnitude and direction of the net force acting on a stone of mass 0.1 kg just after it is dropped from the window of a train station, just after it is dropped from the window of a train running at a constant velocity, so on and so forth. Yeah, try, think about it. Okay, so we have a stone. Mass is given as 0.1 kg, sorry, stone with a mass of 0.1 kg. We need to find the magnitude and the direction of the net force acting on a stone. So just after it's dropped from the window of a train station. So we have the stone and the train is stationary and so on and so forth. So we have the gravitational pull acting on it, and this will be your force. Force on the stone by the net force basically will be 1 minus 1 J cap Newton. So magnitude of the net force is 1 Newton. While the direction is in the negative or downwards. Okay, then just after it is dropped from the window of a train running at a constant velocity. If we have the train moving, so if it's already moving and then the stone is dropped, what will happen? Nothing. Everything remains the same. Just after it is dropped from a window of a train, accelerating with 1 meter per second square. So magnitude and direction of the net force acting on a stone. Say here in case C, the train is accelerating. Train itself is moving faster and faster every second. But if we drop a stone from the window of a train accelerating with 1 meter per second, after you drop it, right, just after it is dropped from the window of a train. So after that drop, after you let it go, okay, even then the answer remains the same. See, the point is you need to have things in touch, things in contact for you to figure out any kind of, for you to act any kind of force, at least contact force. Of course, gravity is a non-contact force. Talking about contact force. When you're dropping and all of that, those are example of contact force. Lying on the floor of a train which is accelerating with 1 meter per second, the stone being at rest with respect to the ground. Okay. So we have the stone. So this is train floor. And the rock is over there. Right? Say this is inside the bogie. And the train itself is accelerating, moving faster. Now they're asking what is the force acting on it. So now we have a different answer. Say it's quite simple. If this is a stone, okay, so please don't get confused with this diagram. If this is the stone and you have the train moving forward, right? Okay, so the train is accelerating and the stone is on the train, accelerating with it. So this is accelerating with this force, with this acceleration. And so for it to accelerate, there needs to be a force acting on it. Along with this, there is gravitational pull as well. Okay, so this is a scenario. In other scenarios wherein you're dropping it in a stationary train, or you're dropping it in from a train which is already moving, or dropping it. Yes, this train is accelerating, but you're dropping it and then looking at the force acting on it. But in this case, it's in the train which is accelerating. Okay, I hope you guys can see the difference. So the first three, the answer is the same, because once you let it go, the only force that is acting on it is gravity. But here it is not so. So we have gravity and the train pulling it forward and the gravity pushing it down. So the force that act on the stone include the forces that act on the stone include, one is gravity and the other is train. Force by the gravity will be 0.1 into 10 j cap, right? If I take up and right as positive, meter per second. Okay, and this is negative. This is -1 j cap meter per second. And we have the force by the train, which is accelerating at 1 meter per second square. So this is 0.1 into 1 I cap. Sorry, not meter per second. What am I telling? I'm still in the Newton. Right. So this would be so many Newton. So minus 0.1 j cap Newton. Sorry, plus. It's to the right, so it's plus. And we have the net force is the sum of this two. This will be 0.1 I cap minus j cap Newton. And the magnitude will be so 1 plus 0.1, so root of 1.01. It's 1.001, actually 1.005 Newton. Okay, and then what do we have? We have the direction, I guess. No, only magnitude is needed. Right, and the angle, direction of the, yeah, we do need the direction. So tan or theta is equal to tan inverse of, you have your y component. Y component is -1 and the x component is 0.1. So tan inverse of 10, that is minus tan inverse of 10. 84.3 degree. So basically it will be pointing down and to the right. So I'll do it here itself. I don't have space over there. It'll be something like this. Yeah. So it would be something like this. So this will be your 84.3 degree. And this is your 1.01 Newton. That's your resulting force. That makes sense. There's a lot more pull force than the push force. That's your answer. Oh, my bad. Acceleration is not 0.1, it's 1. But the mass is 0.1. Okay. Now it's correct. Mass is 0.1. Okay, guys.